There is currently no information available indicating that Mike Holt's grounding versus bonding series featured in EC&M will be published as a standalone textbook. However, there are several textbooks that cover the topics addressed in Mike Holt's series. Firstly, Grounding and Bonding for Electrical Installations by G. L. Johnson. Secondly, Grounding and Bonding, a Comprehensive Guide by Charles M. Oldham. Thirdly, National Electrical Code 2023 Grounding and Bonding by Charles J. Hart. Fourthly, Grounding and Bonding for Electrical Systems by Dave Fisher and Robert J. Mellert. Fifthly, Electrical Grounding and Bonding by Philip A. Stock. These textbooks provide in-depth coverage of grounding and bonding principles, electrical safety requirements, and industry best practices. They are suitable for electrical professionals, apprentices, and students studying electrical codes and installations. Grounding and bonding are essential concepts in electrical engineering, ensuring safety and proper operation of electrical systems. Grounding provides a path for fault current to return to the source, allowing overcurrent devices to operate and clear the fault. Bonding connects non-current carrying metal parts to create a low impedance path for fault current, minimizing the risk of electric shock. Grounding systems are designed to protect people and equipment from electrical faults. A properly grounded system provides a low impedance path for fault current to flow back to the source, tripping circuit breakers or blowing fuses to quickly de-energize the circuit. There are several types of grounding systems, including solid grounding, resistance grounding, and impedance grounding. Solid grounding directly connects the neutral point of the power source to ground, providing a very low impedance path for fault current. Resistance grounding uses a resistor to limit the amount of fault current that flows to ground. This can help to reduce the severity of ground faults and prevent equipment damage. Impedance grounding uses an impedance, such as a reactor, to limit the amount of fault current that flows to ground. This can provide a higher level of protection than resistance grounding. Bonding is the process of connecting all non-current carrying metal parts of an electrical system together to create a low impedance path for fault current. This helps to ensure that all metal parts are at the same potential, reducing the risk of electric shock. Bonding is typically achieved by using bonding jumpers, which are wires or straps that connect metal parts together. The size of the bonding jumper is determined by the size of the circuit conductors. The National Electrical Code, or NEC, provides specific requirements for grounding and bonding electrical systems. These requirements are designed to ensure the safety of people and equipment. Some of the key NEC requirements for grounding and bonding include grounding electrode systems, equipment grounding conductors, bonding of metal enclosures, and grounding of separately derived systems. Grounding electrode systems provide a connection to the earth, providing a path for fault current to flow back to the source. The NEC specifies the types of grounding electrodes that are permitted, as well as the requirements for their installation. Equipment grounding conductors provide a path for fault current to flow back to the source from non-current carrying metal parts of equipment. The NEC specifies the size and type of equipment grounding conductors that are required for different types of equipment. Bonding of metal enclosures ensures that all metal enclosures are at the same potential, reducing the risk of electric shock. The NEC specifies the requirements for bonding metal enclosures, including the use of bonding jumpers and bonding bushings. Grounding of separately derived systems, such as generators and transformers, requires special consideration. The NEC specifies the requirements for grounding separately derived systems, including the use of a grounding electrode conductor and a system bonding jumper. Mike Holt's Grounding vs. Bonding series is currently available to EC&M subscribers in the magazine's digital format. It is also accessible through the EC&M website for registered users. If you are not an EC&M subscriber, you can purchase individual issues of the magazine that contain the series. You can also contact Mike Holt Enterprises directly to inquire about purchasing a reprint of the series. Grounding and bonding are critical for electrical safety. Understanding the principles of grounding and bonding and complying with the NEC requirements is essential for all electrical professionals. Let's delve deeper into the specifics of grounding electrode systems. According to the NEC, a grounding electrode system must consist of one or more of the following electrodes. Firstly, a metal underground water pipe that is in direct contact with the earth for at least 10 feet 3.0 meters, including any metal well casing bonded to the piping. Secondly, a ground ring encircling the building or structure, buried directly in the earth at a depth of not less than 2.5 feet 762 millimeters, and consisting of at least 20 feet 6.1 meters of bare copper conductor not smaller than 2 AWG. Thirdly, a concrete encased electrode consisting of at least 20 feet 6.1 meters of either bare or zinc galvanized or other electrically conductive coated steel reinforcing bar or rod of not less than 1/2 inch 12.7 millimeters in diameter, or at least 20 feet 6.1 meters of bare copper conductor not smaller than 4 AWG. The reinforcing bar or rod must be encased by at least 2 inches 50.8 millimeters of concrete and be located within a concrete foundation or footing that is in direct contact with the earth. Fourthly, a ground rod or pipe electrode. Rod electrodes must be at least 8 feet 2.44 meters in length and must be driven into the ground to a depth of at least 8 feet 2.44 meters. Pipe electrodes must be at least 3/4 of an inch trade size and must also be driven to a depth of at least 8 feet 2.44 meters. Fifthly, plate electrodes must have a surface area of at least 2 square feet 0.186 square meters and must be buried at least 30 inches 762 millimeters below the surface of the earth. The NEC also specifies the requirements for the grounding electrode conductor, which connects the grounding electrode system to the electrical system. The size of the grounding electrode conductor is based on the size of the service entrance conductors. Now let's explore the requirements for equipment grounding conductors. Equipment grounding conductors provide a low impedance path for fault current to flow back to the source from non-current carrying metal parts of equipment. Equipment grounding conductors can be wires, raceways, or other conductive paths. The size of the equipment grounding conductor is based on the size of the circuit conductors. The NEC also specifies the types of equipment grounding conductors that are permitted, as well as the requirements for their installation. The NEC requires that all metal enclosures be bonded together to ensure that they are at the same potential. This reduces the risk of electric shock. Bonding can be achieved by using bonding jumpers, which are wires or straps that connect metal enclosures together. The size of the bonding jumper is determined by the size of the circuit conductors. The NEC also specifies the requirements for bonding bushings, which are used to connect metal conduits to metal enclosures. Separately derived systems, such as generators and transformers, require special consideration for grounding. The NEC specifies the requirements for grounding separately derived systems, including the use of a grounding electrode conductor and a system bonding jumper. A grounding electrode conductor connects the separately derived system to a grounding electrode, such as a ground rod or a metal water pipe. A system bonding jumper connects the neutral conductor of the separately derived system to the equipment grounding conductor. The NEC provides detailed tables and examples to help electrical professionals properly size grounding and bonding conductors. One important table is NEC Table 250.122, which provides the minimum size of equipment grounding conductors for different sizes of overcurrent protective devices. Another important table is NEC Table 250.66, which provides the size of the grounding electrode conductor for different sizes of service entrance conductors. It's crucial to understand that proper grounding and bonding are not only essential for safety, but also for the reliable operation of electrical equipment. Improper grounding and bonding can lead to equipment malfunction, premature failure, and even fire hazards. Therefore, electrical professionals must be diligent in following the NEC requirements and best practices for grounding and bonding. Regular inspections and testing of grounding and bonding systems are also important to ensure that they are functioning properly. Grounding electrode resistance testing can be used to verify the effectiveness of the grounding electrode system. Continuity testing can be used to verify the integrity of bonding connections. In addition to the NEC, other standards and guidelines provide information on grounding and bonding. These include IEE standards, UL standards, and manufacturers' recommendations. Electrical professionals should be familiar with these resources and use them to supplement their knowledge of grounding and bonding. Understanding the difference between grounding and bonding is crucial. Grounding connects the electrical system to the earth, providing a path for fault current to flow back to the source. Bonding connects non-current carrying metal parts together to create a low impedance path for fault current. While both grounding and bonding are essential for safety, they serve different purposes. Grounding protects against electrical shock by providing a path for fault current to flow back to the source, tripping the overcurrent protective device. Bonding protects against electrical shock by ensuring that all metal parts are at the same potential, preventing a person from becoming part of a fault current path. In summary, grounding and bonding are critical aspects of electrical safety and system performance. Electrical professionals must have a thorough understanding of the principles of grounding and bonding, as well as the NEC requirements and best practices. By following these guidelines, electrical professionals can help to ensure the safety of people and equipment and the reliable operation of electrical systems. Always consult with a qualified electrical engineer or inspector if you have any questions or concerns about grounding and bonding. Furthermore, consider continuous professional development to stay up to date on the latest codes, standards, and technologies related to grounding and bonding. This field is constantly evolving, and it's important to remain informed to ensure the highest level of safety and competence. One often overlooked aspect of grounding and bonding is its impact on sensitive electronic equipment. Improper grounding and bonding can lead to voltage fluctuations, noise, and other electrical disturbances that can damage or disrupt the operation of sensitive electronic devices. Therefore, special attention should be paid to grounding and bonding in facilities that house sensitive electronic equipment, such as hospitals, data centers, and research laboratories. This may involve the use of isolated grounding systems, shielded cables, and other specialized techniques to minimize electrical noise and interference. Another important consideration is the grounding and bonding of renewable energy systems such as solar photovoltaic, PV systems, and wind turbines. These systems often have unique grounding and bonding requirements that must be carefully considered to ensure safety and proper operation. The NEC provides specific requirements for grounding and bonding renewable energy systems, and electrical professionals should be familiar with these requirements. For example, solar PV systems typically require a separate grounding electrode system that is independent of the building's grounding electrode system. This is to prevent ground faults in the PV system from affecting the building's electrical system. Wind turbines also have unique grounding and bonding requirements due to their large size and exposure to the elements. It's important to consult with a wind turbine manufacturer and a qualified electrical engineer to ensure that the grounding and bonding system is properly designed and installed. In addition to the technical aspects of grounding and bonding, it's also important to consider the human factor. Electrical professionals must be properly trained and qualified to perform grounding and bonding work. They must also be aware of the potential hazards involved and take appropriate safety precautions. This includes wearing appropriate personal protective equipment, PPE, such as gloves and safety glasses, and following lockout-tagout procedures to de-energize circuits before working on them. It's also important to communicate effectively with other workers and building occupants to ensure that they are aware of the potential hazards and take appropriate precautions. Grounding and bonding are not just theoretical concepts. They are real-world practices that have a direct impact on the safety and well-being of people. By taking the time to understand the principles of grounding and bonding and following the NEC requirements and best practices, electrical professionals can help to create a safer and more reliable electrical environment for everyone. Keep in mind that electrical codes and standards are subject to change, so it's important to stay informed of the latest updates. The NEC is typically updated every 3 years, and electrical professionals should make sure that they are using the latest version of the code. There are also numerous online resources and training programs available to help electrical professionals stay up to date on grounding and bonding. These resources can provide valuable information and insights into the latest technologies and best practices. In conclusion, grounding and bonding are essential components of a safe and reliable electrical system. By understanding the principles of grounding and bonding, following the NEC requirements, and staying up to date on the latest technologies and best practices, electrical professionals can help to ensure the safety of people and equipment and the reliable operation of electrical systems. The information presented here serves as a general overview and should not be considered a substitute for professional electrical engineering advice. Always consult with a qualified electrical engineer or inspector before making any decisions about grounding and bonding. Proper grounding and bonding also mitigates electromagnetic interference (EMI). EMI can disrupt sensitive electronic equipment. Therefore, attention should be put to grounding in facilities housing computer systems, medical equipment, and communications systems. Also, surge protection devices, SPDs, are often used in conjunction with grounding and bonding to protect equipment from voltage surges caused by lightning strikes or other transient events. SPD diverts surge current to ground, preventing it from damaging sensitive equipment. Effective grounding and bonding are essential for SPD to function properly. They provide a low impedance path for the surge current to flow to ground, minimizing the voltage surge experienced by the protected equipment. Understanding the different types of grounding systems is also important. Common types include solidly grounded systems, impedance grounded systems, and ungrounded systems. Solidly grounded systems connect the neutral point of the power source directly to ground. This provides a low impedance path for fault current, allowing overcurrent devices to quickly clear faults. Impedance grounded systems use a resistor or reactor to limit the amount of fault current that flows to ground. This can help to reduce the severity of ground faults and prevent equipment damage. Ungrounded systems do not have a direct connection to ground. While ungrounded systems can offer some advantages in terms of service continuity, they also have some disadvantages, such as the difficulty of locating ground faults. In addition to the NEC, other standards and organizations provide guidance on grounding and bonding. The Institute of Electrical and Electronics Engineers (IEE) publishes standards on grounding and bonding for various applications, including power systems, telecommunications systems, and electronic equipment. Underwriters Laboratories also publishes standards on grounding and bonding for electrical products. Furthermore, manufacturers of electrical equipment often provide recommendations on grounding and bonding their product. The knowledge of these resources can greatly help in grounding and bonding practices. It is very important to consider the specific application and environment when designing a grounding and bonding system. For example, a grounding and bonding system for a hospital will have different requirements than a grounding and bonding system for a factory. Factors to consider include the type of equipment being used, the sensitivity of the equipment to electrical noise, and the presence of hazardous materials. In hazardous locations, such as those where flammable gases or liquids are present, special grounding and bonding requirements apply. These requirements are designed to prevent explosions and fires caused by electrical sparks. The NEC provides specific requirements for grounding and bonding in hazardous locations. The use of intrinsically safe equipment is also common in hazardous locations. Intrinsically safe equipment is designed to prevent the release of enough energy to ignite a flammable atmosphere. Proper grounding and bonding are essential for intrinsically safe equipment to function properly. Also consider the impact of corrosion on grounding and bonding systems. Corrosion can degrade the performance of grounding and bonding connections, leading to increased impedance and reduced effectiveness. Therefore, it's important to use corrosion-resistant materials and construction techniques when installing grounding and bonding systems. Regular inspections and maintenance of grounding and bonding systems are also important to identify and address any signs of corrosion. The use of exothermic welding, also known as CAD welding, is a common technique for creating permanent, corrosion-resistant grounding and bonding connections. Exothermic welding involves using a chemical reaction to create a molten metal connection between two conductors. This connection is stronger and more corrosion resistant than mechanical connections. The topic of grounding and bonding also involves understanding the concept of impedance. Impedance is the opposition to the flow of alternating current, AC. It is similar to resistance in direct current (DC) circuits, but it also takes into account the effects of capacitance and inductance. A low impedance grounding and bonding system is essential for providing a safe and effective path for fault current. High impedance grounding and bonding systems can lead to increased voltage drops, reduced fault current, and increased risk of electrical shock. Always remember to properly document the grounding and bonding system. Documentation should include drawings, specifications, and test results. This documentation can be useful for troubleshooting problems and for future maintenance and upgrades. Consider performing regular audits of the grounding and bonding system to ensure that it is still in compliance with the NEC and other applicable standards. An audit should include a visual inspection of the grounding and bonding connections, as well as testing of the grounding electrode resistance and bonding impedance. It is crucial to understand the relationship between grounding, bonding, and surge protection. All three are important components of a comprehensive electrical safety strategy. Grounding provides a reference point for the electrical system. Bonding ensures that all metal parts are at the same potential. Surge protection protects equipment from voltage surges. When properly coordinated, grounding, bonding, and surge protection can provide a high level of protection against electrical hazards. In areas with high lightning activity, it's especially important to pay close attention to grounding and bonding. Lightning strikes can cause significant damage to electrical equipment and can also pose a serious safety hazard. The use of lightning protection systems, LPSs, in conjunction with grounding and bonding can help to mitigate the risks associated with lightning strikes. These systems typically consist of air terminals, DAN conductors, and a grounding electrode system.